First of all, I'm very honored to be the first speaker at this meeting. I was actually going to be the first speaker until there was airline chaos, and I really apologize that at the end had I taken the plane, I probably wouldn't even be here this morning with you. The organizers very kindly asked me to give the talk over Zoom, which I'm very honored to do. I also want to thank the organizers very much for all of the excellent arrangements that have been made, and also for the great lineup of people talking at the meeting. So I'm going to talk about, something perhaps a little bit different than we normally think about, and this is essentially non-equilibrium quantum matter. And as you can see, the title is refers to the quantum matter we're looking at, and that's actually a pumped magnon condensate. So the collaborators are here. Of course, nothing would have happened without them. So especially important were the two postdocs. One is experimentalist Joe Bailey, and the other is Pablo Suchkachov, who is a postdoc with Sasha Belatsky from Connecticut and Sweden, and it was funded by ERC. So, of course, something that this audience hardly needs to be told about is this ubiquity, growing ubiquity of multiband superconductivity. Actually, multiband superconductivity started before high TC was discovered, the cuprates were discovered, and actually you'll notice some of the same people. There's Bednorz here at the bottom, and then of course Binnig, who after this work actually decided to invent the STM, is the first author. And what they looked at was something that has recently undergone a bit of a revival, which is niobium doped or generally doped strontium titanate. And what they discovered then was it looked as if there was two gaps and actually two evolutions of the chemical potential as you dope this material, and you get actually an order parameter which is essentially consists of two coupled superconductor associated with the two different bands. Of course, if I flash forward ahead, and this is really taking close to Newcastle, of course, iron selenium is, of course, another nowadays a well-known host of two different types of orbitals with essentially two superconducting order parameters which develop together in this relatively simple lattice. And so multiband superconductivity has been with us for a while. And I should also say that it's not just in bulk materials, but also in these oxide interfaces. And again, you can get, and it's very nicely schematized in this Nature Materials article by Hilgenkamp and collaborators. That's here in the right-hand corner, is you have essentially a Lifshitz transition where you initially have essentially, if you add electrons, you first populate one band, then you start populating another band. And as you populate these two bands, actually, then you get this possibility of having a multi-condensate superconductor. And so this is very nice. And the question about this, what one might ask is, these multi-band condensates, do they exist just for essentially superconductors charged superfluids, just for paired fermions? The other thing is these things are pretty exotic, and you generally have to go to low temperatures, and you'd like to know whether you can access this type of behavior at more convenient temperatures, for example, room temperature. And the last thing is, of course, all of this stuff that I just told you about is essentially tuning chemistry, which is nice if you are a grower or a chemist. But is there some other more direct way that you could actually get into a multiband superconducting or superfluid state. So these are the questions that uh, essentially this research is based on that I'm going to describe to you. And so the condensates that I'm going to talk about are bosonic condensates. And of course, and the bosonic condensates where they're actually very natural multiband phenomena. Of course, uh, magnons, of course, if there's more than one type of atom per unit cell, of course, you have several bands of magnons. Uh, but let's just start with a single band. So here I've basically a single band of magnons, and they obey some kind of Landau-Lifshitz Gilbert equation. And it's, of course, here I'm just writing down that precession equation. And if effectively, you could try to imagine these magnons as bosons, which you could pump up and have just a conventional type of BEC. And this BEC here arises essentially because of the competition between the exchange and dipole interaction. So in particular, if you look here over at the right, there's a minimum in the dispersion surface for typical magnons in strong ferromagnets like yttrium iron garnet, which is coming about because of a competition between the exchange interaction and the dipole interaction. And the idea is that you have this ferromagnet, which has, of course, ordering at Q equals 0, and you can then essentially pump that ferromagnet at the ferromagnetic resonance frequency, which is, of course, a long wavelength thing. And if you pump enough magnons into that at that resonant frequency, you could actually then, those magnons can then degenerate into magnon pairs, which have finite momentum. And after a time, of course, if you have enough of these finite momentum magnons, they accumulate essentially at this momentum vector, which is at the minimum of this of the dispersion curve. So you have actually the possibility here to create a pumped magnon condensate simply by increasing the population of conventional magnons at Q equals 0. And so it's a fact, and this has been known now, these original experiments were published almost 2 decades ago by Demokritov in Nature, this reference here at the bottom of the page. And this parametric pumping process basically is very efficient. And these magnons are extremely long-lived, so they act essentially like, quasi-particles which are long-lived. Which then scatter down to this minimum where they then sit. And effectively, this pumping corresponds to raising the chemical potential. And what these people did in 2006 was identify at a critical pumping level, identified a Bose condensate of magnons. And just to tell you a little bit more about this material, this host for the magnon BEC is yttrium iron garnet. It's basically this complicated chemical formula. It's cubic. It's extremely unusual in that it has the lowest reported magnon damping of any material. So it's basically a Q of essentially 10 to the fifth, which means that these quasi-particles that wind up in the Bose condensate are extremely long-lived. More common magnets like permalloy are much worse. I mean, it's 3 orders of magnitude worse. I should also say that actually it's a bit of an unsolved problem in magnetism why this material has this pathologically high Q, because it's really quite singular. And because actually this material has this extremely high Q, which enables Q'd experiments like BEC of magnons, it's also been for a long time of big technological relevance, for microwaves and magneto-optics. And of course, more recently, people have been doing spintronics and quantum technologies, for example, coupling these magnons to individual superconducting qubits. So in essence, what's actually happening here? How do we go now from this single magnon or single BEC to a multi-component BEC? And of course, the way we do it is exactly the same way we do it with the electronic multiband superconductors. Is we go to a multiband situation, and the way we do this multiband single particle situation is very simple. We go to finite thickness samples or slabs of yttrium iron garnet. And what you'll find is, of course, you'll find a set of symmetric and antisymmetric eigenstates of the Landau-Lifshitz-Gilbert equations, which correspond to essentially odd and even parity spin wave oscillations. And I've shown you here the solutions here for yttrium iron garnet. This is in gigahertz, and this is the momentum transfer. And you see these different gaps, okay, the spin waves, and then you also see the different bands. Now, the lowest band, okay, which is the one we've of course has been looked at before, has this rather pronounced minimum in the dispersion out here. If you go to the next bands, they still actually have slight minimum, which are rather hard to see. And then you go up, of course, to the really the higher line ones, and those, of course, don't have the minimum. So what one can hope to do, and this is the experiment that we set out to do, is to see if we could get a multi-band condensate involving essentially these two, the n equals 0 and the n equals 1 eigenstates. And of course, here they're drawn out essentially as you would in a quantum well. Okay. And so the first thing to check is, of course, if these pictures that I drew here of multi-band spin waves are actually correct. And the technique that we use to measure these spin waves is Brillouin light scattering. So it's basically, for these purposes, very similar to neutron scattering. Of course, the wave vectors are much smaller, but you essentially get some kind of a density of states at the momentum vector, which is close to 0. That corresponds to the laser light wavelength, which is 473 nanometers in this case. So this shows actually the spin wave spectrum, actually showing the n equals 0 and n equals 1 modes. There's also actually something in between these two, and that's actually multi-magnon scattering. But the fact is, you can see in this plot, you can see the two expected peaks for the bottom, essentially, of the magnon bands for the n equals 0 basically the lowest order one plus the first odd order one. And the next thing to do, so that's just without microwaves. That's just the thermal equilibrium spin fluctuations. And so now the recipe is actually quite simple. We are just going to do what Democritoff and his colleagues did a long time ago, and actually add microwaves to this problem. And what we have here is a very, very narrow strip line, basically, which is very close to this sample, and of course the fields, the microwave fields, and the external field are defined actually in this way here. So this is just a blow up of this bridge structure that was built by Joe Bailey. So what happens when we start pumping harder with the microwaves through these strip lines? So let me take you again through to the Brion scattering, which is in the top frame. And what I've shown you here is just what happens thermally, what the light scattering spectrum looks like when I have just thermal magnons and two magnons at 300K. Now, what I'm going to show you, and this is very important to keep track of this. This is a linear scale, so these are very, very small intensities. We start pumping with microwaves. Then actually what happens is you no longer get this peak, actually, these the shoulders being terribly prominent, but actually you start to grow, actually after a while, you start to grow a very, very significant peak here at this frequency here in the middle. And that's, of course, just the pump frequency that you're applying. But in addition to growing intensity as you increase the intensity of the pump, first at this frequency, okay, so you're basically operating at a frequency here of 3.4 gigahertz. So you're pumping it roughly in the middle. And as you just get back essentially what amounts to essentially magnons at that frequency. If you exceed a particular threshold, a particular pump power, you suddenly start to see these sidebands, and you actually see two sidebands, not one. And these two sidebands actually wind up showing up actually slightly below the frequencies that you saw at zero microwave power, and the other one is slightly in the vicinity of this frequency. So what you're seeing here is, of course, the magnons that are appearing because of the BEC. And this is happening very, very suddenly. So let me just show you down here, just to remind you, this is a log scale here. This is the same logarithmic scale. And what you're finding here is that if you go to what we call the n equals 0 BEC formation, this is the lower frequency of these two. You suddenly, if you have to go above something like 29 or so dBm, you suddenly see an onset of essentially condensate there. That essentially corresponds to magnons in that minimum. And actually, around the same time, which is a bit surprising, you see also condensate in n equals 1. Now, what's of course happened before that is this increase here is what you see at the peak in the middle. In other words, at the frequency at the driving frequency. And what this represents is essentially the ability to create magnon pairs precisely, basically at the driving frequency. In other words, two magnons whose energy is actually equal to the driving frequency. So this is showing you now that you actually have a double magnon condensate. So both of these bands, which we pointed out in the previous slide, are actually quite different. These bands actually, even though this minimum here is very shallow, both of these bands are suddenly actually seeing an occupancy, basically condensates. So this is very exciting. So let me just take you through this magnon pair formation, which is this peak in the middle. And then after you've started forming these pairs, then you pump some more, you eventually then get these two condensates, which appear at the same time. And so actually, there's a huge amount of data here. And having now just walked you through the basic phenomenon, one can do a lot of data analysis. And actually, what I'm showing you here is how these magnons, actually these condensates, and also magnon pairs decay as a function of time. So what I can do is I can prepare based as I do actually when I do atoms in traps or BEC condensates with cold atoms. Of course, I prepare the the atoms, I make them very cold, and then they condense, and then of course eventually it's an out of equilibrium situation, and the condensates die. And one can now ask the same kind of question that the atomic physicists ask is, how does this, first of all, what happens after I've pumped up this condensate or I've created this out of equilibrium condensate, and how long does it last? And so what I'm showing you here is essentially very similar data to what I just showed you before, but now I'm showing it to you as a function of time after the microwave pulse. And what you're seeing right now is what happens after almost a microsecond. Of course, now everything is gone. I'll just let it start again and walk you through this. I hope it stops soon. I think it should. It's going a little bit longer than I hoped. Okay, there. Now it's at the beginning. Now we're pumping. Now we're within the first 500 nanoseconds. Now I can see in the middle the parametric pumping occurring, and now suddenly you're seeing the condensates appear later. Okay, and now after you turn off the pump, what you see is that the parametric stuff goes away very fast, but the condensates actually are stable, are quite stable. So you can still see at the green arrow and the blue arrow that there's something left, even well after the 500 nanoseconds has passed. So just static pictures of this. I'm just showing you now different cuts of the data. This is frequency and time. These are color plots of these Briand scattering intensities. And here what we're doing is we're varying actually the frequency of the microwave pumping. So if we just pump at 6.45 gigahertz, of course, there's a kinematic constraint, right? I have to create magnon pairs that then go into these minima. Of course, it's possible that I will not be able to create, I will be below the threshold of creating such pairs. But in any case, here at 6.45 gigahertz, I can pump the system up and I get a nice two magnon response. Notice here, of course, I'm pumping at 6.45. And then I'm seeing pairs of magnons, basically, each with a frequency of 3.25. And then if I shut off the microwaves, then essentially everything is gone. Now, if I go to 6.55 gigahertz, I can start to see that there's actually something appearing down here, which is closer to the minimum of the dispersion surface. So remember, this energy here is of course, half the pump. And here we're dealing again with the energy here being half the pump, but then now half the pump actually then allows me actually to probe towards the minimum. If I then increase the frequency more, I can see that I can pump my magnons, just pairs of magnons, magnon pair creation, but I also get magnons actually, I also start to get magnons near the minima of the dispersion surfaces. And these minima here in this dispersion curve last a lot longer than just the raw pairs of magnons that are created by the microwaves. And then if I go up to 7 gigahertz, actually, I can no longer, I basically just get a broad continuum here, which more or less terminates at the same time as the two magnon peak terminates here. And of course, one can now refine the analysis some more, and one can do essentially time scans through these just to validate the qualitative conclusions that we can find from looking at these color plots. And indeed, what you see here is on these, for instance, this blue curve here, okay, corresponding to this magnon minimum. Okay, this condensate, you can see this lasts an awfully lot longer than this just simple two magnon population at half the pumping frequency. And of course, if you go above resonance, then all these decays again fall into line. So another way to cut this. So I've been cutting this in very many different ways. this is now sort of relevant here for the kinematics. What I've got on the vertical axis is essentially the observation frequency, in other words, the frequency transfer in the Briand scattering, and along this axis I have the pump frequency. And what you can see here is essentially that there is some kind of a kinematic resonance condition for the appearance of these two condensates. So initially the condensates don't appear, but interestingly enough, the two pair condensates are coupled. They appear at the same time. And of course, one can look at these data again much more quantitatively. But what you have here again is just the blow up of essentially what I showed you before is at an optimal. There's an optimal frequency for this these independent condensates appearing, and that seems to be around 6.7 gigahertz. And at that optimal frequency, you get actually very long-lasting two component condensate, basically with the n equals 0 and n equals 1 magnons appearing and disappearing more or less simultaneously. Now, I don't want to take too much of more of your time. We can actually analyze all of these data. Actually, the dynamics of formation of the condensate is also very dependent on the frequency and the power. I don't want to talk about that because I think it's essentially all of the interesting physics really is summarized by the fact that you have a very, very long-lived set of magnons appearing as part of a condensate, and these magnons have frequencies which are quite different from half of the pump frequency which created the pairs in the first place. And this again shows these decays, and let me now show the kinematics of this condensate basically in line plots rather than color. So what I'm showing you here are essentially the amplitudes and the lifetimes of the two condensates, as well as, of course, the lifetimes of simply the pump, which it simply exists, the magnons that exist at precisely half the pump frequency. And what you can see, and again, for reasons of time, let's just focus on the right-hand side the slide here. What you'll see is that we have a resonance effectively at 6.7 gigahertz. That's where these condensates, both of them live the longest, and then afterwards, actually, they don't live as long anymore, although they still live, especially the n equals 0 one lives quite a bit longer than the pump magnons, the pair magnons. Now, there's another thing that happens actually, is that these decays actually are not strictly exponential. And in fact, they deviate the most from exponential when you get close to resonance. I'm not going to talk about the detail of that, but I'm now just going to talk a bit about the physics. So where does this resonance come from? And in particular, how am I to think about this in terms of the things that I showed at the beginning for the electrons? So what I'm showing you here at the left are the dispersion surfaces for the n equals 0 and n equals 1 mode. So the n equals 0 mode is the blue, is this blue surface. The n equals 1 mode is this green surface. And what seems to happen, of course, is when we generate magnons or magnon pairs at q equals 0, could they have opposite momenta? And there are actually two ways in which they can have opposite, they basically can have opposite momentum. One way is, of course, if they stay within, let's say, the n equals 0 dispersion surface. In other words, they're selected from essentially there are two opposite wave vectors on that surface. But there's another way, of course, that you can get essentially average the momentum to zero. And that's in fact, if you essentially create one magnon in the lower dispersion surface and another magnon in the upper one. In other words, you have an n equals 1 and an n equals 0. So what you have essentially in this state is if you wish, a bound state of basically a magnon, and n equals of one band of magnon and another band of magnon. And of course, that condition, because you have to divide the momenta equally, and also you have to divide the energy, that is optimized actually more or less at exactly half at the midpoint between these two dispersion surfaces. And that indeed is actually why, and this calculation here looks at that factor in diagrammatic form, that is in fact why you actually expect that the phase space is most favorable for forming a two magnon condensate, or even a single magnon condensate, when you're precisely here in the middle. And that gives you this resonance. So this actually gives you not only a resonance, but it also tells you that the optimal superconductivity, or the optimal superfluidity in this case, is actually two bands, not one band. And in fact, you benefit enormously from two bands. Now, what's quite similar, of course, to some of the solid state systems that I showed you, where you find the same thing happening in the form of Lifshitz points, where essentially you start crossing over. When you start, let's say, filling a system with electrons, and suddenly you've filled one band, you start filling another. That's quite often a very good place for multiband superconductivity. So this is very much analogous to that. I'm not going to take you through this, but I think I'm going to head right towards the conclusions, and just summarized that we have multiband condensates now. We have a model system which is actually realizable at 300 Kelvin and with relatively simple microwave and optical diagnostics. And I can answer actually all of the questions that I raised at the beginning of the talk. And the first question, of course, is, do these condensates exist just for fermion pairs, for superconductors? Actually, that's not true. They actually also exist for multiband boson systems, in particular the yttrium garnet system that I showed today. The next question is, can we access these at more convenient temperatures? Yes, we can. This is all room temperature. And the third thing is for this particular multiband condensate, we have control parameters that really don't depend on accidents of chemistry. We have pump power, external magnetic field, pump frequency, and sample thickness, all of which actually can be modulated to look at the phase diagram. And in fact, I can show you here a phase diagram for this system where we varied both the pump frequency. Remember, the pump frequency is, of course, crucial for defining the kinematics, because I said that resonance, of course, is particularly favored when you're more or less halfway between the n equals 0 and n equals 1 bands. And then pump power, which is obviously, chemical potential, sort of how much stuff how many magnons you have. And this just shows actually a phase diagram that we drew. It turns out that actually pump frequency and external field are actually very similar parameters. But the most important thing is that we have a phase diagram. And we have a phase diagram which basically first gets parametrically pumped pairs at half the pump frequency. And then there's actually a coexistence region for condensates. But there's actually also regions we found in the phase diagram where we have only one type of condensate or the other type of condensate. So this looks very much like material science, but actually it's all just the varying things that you have in the basically just varying power and frequency and external field. So thank you very much.
Thank you very much, Gabe, for this very interesting talk. Maybe we have time for a short question. Could you, since we don't have a microphone, can you come here so he can hear? Thank you so much.
Thank you.
So this is Han Chu.
Oh, excellent, like great, exciting talk. Quick question is there any actual experiment evidence of like this two particle bond state as you mentioned? And will be the next experiment evidence of, let's say, coherence?
Well, the coherence is, of course, measured directly because these lifetimes are very long. Okay. And you have to realize that let me just show you the data, the raw data here. These are logarithmic scales. And so these are actually quite very sharp peaks. So this is, when you pump up these condensates, you're dealing with, this is more than an order, this is more than an order of magnitude here. So these are actually very sharp peaks in frequency, which correspond, of course, to the minima in the dispersion curve. But not only that, you of course the existence of this bound state is of course implied by the very sharp peak in the, let me just show you this again here, by essentially this very sharp peak in the lifetime. So this bound state, which of course you have to realize, you initially have this quasi-bound state because you create a Magnum pair between the lower band and the upper band. And then of course they condense by themselves, but this state then at the end is very coherent and lasts a very long time. So we're dealing here with many with 30 nanoseconds. So this enhancement essentially is the proof that this kinematic picture, which has that bound state, is actually the correct picture.
Got it. Thank you very much.
I think due to the time, we will move on. Thank you so much, Gabe, for this, for this wonderful talk.
Okay. Thank you very much. Okay. Sorry I can't be with you.
We missed your presence, but yes.
Thank you. Okay. Bye-bye.